Have you ever stopped and wondered why you can slap pretty much any operating system you want on a PC, but your phone or maybe a new ARM laptop is totally locked down to just one? Well, it's not just about corporate policy. It gets way deeper than that, down to two completely different ways of thinking about hardware. Today, we're going to get into that tech divide: ACPI versus the device tree. Okay, and let's just kick things off with a real-world cry for help from a developer. Man, this one sentence just nails the whole problem, doesn't it? The reason they can't boot another OS all comes down to one missing file, this thing called a device tree. So what in the world is that, and why doesn't your PC seem to need one at all? And that, right there, is the big question for today. Why is it that the PC you build yourself or buy from any old brand just kind of works with almost any OS you throw at it, while ARM devices, your phone, your tablet, that shiny new dev kit, are all their own little locked-down islands? The answer lies in two competing philosophies for how a computer should understand itself. To really get the difference, let's start with the world we all know best, the personal computer and that amazing promise of universal compatibility. For as long as most of us have been using computers, we've just kind of taken this for granted. You can grab a Windows install disk, download a Linux distro, maybe even try out FreeBSD. And odds are it's going to boot on your Dell, your HP, or that custom rig you built in your garage. This isn't magic. It's the result of some seriously clever, standardized engineering. So what's the secret sauce here? It's a standard called ACPI. The best way to think of it is like a universal translator that's built right into your PC's firmware. When an operating system boots up, it doesn't need some pre-written map of all the hardware. No. It just asks ACPI, hey, what have we got in here? And ACPI dynamically describes every single component, from the CPU cores all the way down to the USB ports. And believe it or not, you use ACPI's handiwork all the time without even realizing it. Every time you put your laptop to sleep, you're actually using a standardized ACPI power state, like S3, which is suspend to RAM. Because these states are part of a standard, any OS knows exactly how to tell any computer's hardware how to power down and, crucially, how to wake back up again. Okay, so that's the dynamic, standardized world of the PC. Now, let's completely switch gears and jump over to the ARM world, which, it turns out, was built on a totally different philosophy. See, ARM processors didn't grow up on a desk. They grew up in the embedded world. We're talking car engines, factory controllers, the guts of early cell phones. In that world, the hardware is totally fixed. It never, ever changes. So the goal isn't flexibility, it's all about raw efficiency. You don't need a universal translator if you're only ever going to talk to one person your entire life. And that's where the device tree comes in. It's not a dynamic discovery tool, it's a static description. It's a literal blueprint, a file that says, okay, for this specific phone model, there's a Qualcomm chip at this memory address, there's this much RAM at that address, and the display controller is connected to these exact pins. And the process itself really shows you how different the thinking is here. First, a developer has to write out a text file describing all the hardware. Then that gets compiled into a binary file, this blob. When the device boots, the bootloader has to find that one specific blueprint and hand it over to the operating system kernel. If it can't find that exact file, the OS is basically flying blind. So we've got ACPI's dynamic, ongoing conversation on one side and the device tree's static, unchangeable blueprint on the other. Let's put these two philosophies head to head to really see what makes them tick. This slide really gets to the heart of it. ACPI gives you dynamic discovery, and it lives inside the computer's firmware. Yeah, it's complex, but the result is a universal standard. Then you have the device tree. It's just a simple, separate file, a static description. It's clean for sure, but since every single device needs its own custom-made file, it leads to a ridiculously fragmented ecosystem. But the story doesn't end there. Once the kernel finds out what hardware it's working with, whether it got that info from ACPI or a device tree, it still needs a consistent way to manage all that stuff. And this is where Linux has a really elegant solution that works on top of both systems. So the kernel has its map, right? It knows there's a USB port here, a hard drive over there. But so what? How does it actually turn that information into something that you or your applications can use? Okay, the first piece of the puzzle is SYSfs. The absolute best way to picture it is as a live dashboard of your computer's hardware, but it's presented to you as a file system. You can literally go into the /sys directory on a Linux machine and browse through every single device the kernel knows about and see all of its properties in real time. It's the ultimate source of truth for the hardware's current state. And if SYSfs is the live dashboard, then udev is the event coordinator. It's this little process that's always running in the background, just watching for events from the kernel. So when a new device shows up, like you plug something in, udev gets the notification and immediately springs into action. So let's trace it. Say you plug in a USB drive. The kernel sees the new hardware and sends out an event. udev catches that event, then immediately goes to the SYSfs dashboard to get all the details. Who made the drive, what model is it, all that good stuff. Then it looks at its own rulebook. And based on those rules, it creates the device file, something like /dev/sda1, so you can actually get to your files. And this whole dynamic system works beautifully on top of both ACPI and device tree. So here we are with these two systems, one that's pretty open but kind of a mess, and another that's clean but often leads to closed-off devices. Neither one is perfect, which brings us to the big question. What does the future of all this look like?
Now, you might be sitting there thinking, okay, ACPI is obviously the winner, right? It gave us the open PC platform we love. Well, not so fast. It is famously notoriously complex and often super buggy. The creator of Linux himself, Linus Torvalds, did not mince words, calling it a complete design disaster. Developers have literally spent years of their lives just writing workarounds for broken ACPI code from different vendors.
But then you look at the device tree, and it has its own really dark side. Because every single device needs its own special, often proprietary blueprint, it becomes the perfect tool for vendor lock-in. A company can just choose not to release the device tree. And just like that, they've effectively blocked any other operating system from ever running on their hardware. The devices are, as the quote says, designed to be incompatible by choice. So in the end, there's just no silver bullet here. It's all about trade-offs. We're kind of stuck between two imperfect choices. The universal standard that's a nightmare to get right, or the simple blueprint that creates a world full of walled gardens. But here's the cool part. The story isn't over. The industry knows this is a problem, and new initiatives like ARM System Ready are actively working to bring that It Just Works promise of ACPI over to the ARM world. The goal is to create a standard so that one day you really can install any OS on any ARM laptop, just like you do with a PC. And this all leaves us with one last big question. In a world where computing is spreading out faster than ever before, are we going to see a convergence? Will we get a single open standard that combines the best of both worlds? Or is the future just more fragmentation, where every single device we own lives in its own separate, incompatible universe? I guess only time will tell.